Hi everyone. Today let's talk about the general solutions of linear equations. So for higher order linear equations, we have the standard form. Okay, the first, oops. All right. We have the highest derivative, the coefficient is 1, that's the standard form. And then we have the lower derivatives. And then we have the coefficient functions, they are functions of x. Okay, so this is high order linear differential equations. And you can see the order is n, okay? The order is n, so the initial conditions, we're going to have n informations. So we have y prime, and y to the n minus 1 derivative at the initial points x0. Okay, so here we have n conditions. Okay, I have ... in between. Okay. So we want to look for an open interval alpha beta containing the initial points x0 where all the coefficients are continuous. Okay, then we have the theorem of existence and uniqueness for linear order ODE. Okay, it guarantees that unique solutions exist at least as large as the interval alpha beta. Okay, for homogeneous equation with the right-hand side, the force functions f of x is 0. The solution space is actually a linear function space of dimension n. So in session 5.1, we already showed this, this linear function space is a vector space of dimension n. So we need n linearly independent solution to describe all the possible solutions. Okay, which is the basics of a vector space. So a basis for this function space. So by closure under addition and scalar multiplication, the general solution is y of x equals to a linear combination of n solutions. So c1y1 plus c2y2 plus ... plus cn yn. Okay, so all of this y1, y2, yn, they are solutions. Okay, and they are linearly independent solutions. Okay, so our general solution is a linear combination of those n solutions in the basics. Okay. All right, so how do we check linear independence? Okay, so similar to what we did for the second order. Okay, so for the second order, we only need C1, Y1, and C2, Y2. But here for nth order, we're going to generalize this idea. So we start with C1, Y1, C2, Y2 plus ... plus Cn, Yn equal to 0. And we try to solve for the Ci's. If all the Ci's are 0, then this guy, if all the Ci's are 0, when we plug in the Ci's, we just get 0 equal to 0. So it means we know nothing about the functions. So no relationship among the functions. So we have linearly independence. Okay, if one of the Ci's are not 0, so one of them is not 0, then we have linearly dependence. Okay. So we have this guy give us 1 equations, and here we have n unknowns. Okay, in order to solve n unknowns, we actually need n equations. So how do we get the other n minus 1 equations? We get them by taking the derivative of these equations on both sides. Okay. So that's why we take the first derivative, we get this guy, we take the second derivative, we get this guy, and the n minus 1 derivative, we get this guy. So together with this guy, we have n equations to solve n unknowns. So this is an n by n system, okay? So we have an n by n matrix, and the unknowns are C1, C2, Cn. And then we have the right-hand side, because this is a homogeneous equation. The right-hand side are just zeros, okay? Because now we have an n by n square matrix, we can compute the determinant. So if the determinant, we also call the Wronskian of those function solutions. Okay, if the Wronskian is not 0, then we know the homogeneous system has a unique solution. The unique solution is also the trivial solution. It means all the CIs are 0. So that's why we get linearly independent. Okay, so let me write down here. So all the CI are 0, we get linearly independent. Okay, if one of the CIs is not 0, so at least one of them is not 0, we get linearly dependent. Okay, yeah, so this is one case, this is the second case. We have two cases. So either linearly independent or dependent. Okay. All right. So today the sessions also involve how to solve a higher order polynomial. Well, we know that for quadratic functions, we have quadratic formula to solve it. How about higher order polynomial equations? How can we solve it? Well, this is the rational roots theorem. Okay, so first of all, we have the leading coefficients a sub n. Okay, so all of these are the coefficients. Okay, and let's look at the leading coefficients and the constant term. Okay, if a sub n and a0 are non-zero, then each rational roots can be written as x equals to p over q, where p is an integer factor of the constant a0. Okay, and q is an integer factor of the leading coefficients a sub n. Okay. All right. What does that mean? Okay. That means, well, when we solve this polynomial, we can, if this polynomial is degree n, ideally we are able to decompose as a factor of n linear factors, where the coefficients are complex numbers. Okay, in complex numbers we can do that. However, if we restrict the coefficients to be real numbers, sometimes, for example, some quadratic functions, they have complex roots, so you're not able to decompose into two linear factors, so it will be just like the quadratic factor. Okay, so this theorem tells us that if this polynomial equation has a rational root, okay, then the rational root must be of this form. Okay, so let me write it down what I just said. Okay, so we mark first. So if the polynomial, shorthand notation, let's say if p of x equal to 0 has rational roots, okay, then all the rational roots must be in this form. Okay, what form? It equals to p over q, where p is an integer factor of the constant term a0, and q is an integer factor of the leading coefficient a sub n. Okay, this is the first remark. Second remark. Okay, so later on when we work on examples, you see actually the p over q. So this form we have many numbers. Okay, so any number of this form might not necessarily be the root. Okay, so even though we have this form, okay, but some of those numbers in this form, so we will get many numbers. So some of those numbers are the roots. Okay, but it might be possible that those numbers are not the roots. Okay, so not all the numbers of these forms are the roots of the polynomial. Okay, but not all. Okay, maybe none of them are roots. That's also possible. Okay, so maybe I should say some of the numbers might be roots, however, but not all of them are the roots of p of x. Okay. All right. So after we also, this is a table that we call what we learned in sessions 5.1. Okay, we learned about how to solve the linear ODE, second order linear ODE with constant coefficients based on whether the roots of the characteristic equations are two roots, one repeated root, or two complex conjugate roots. So here are the formula. Here are the formula for that. Okay. All right, so let's solve our example 1. Okay, so let's solve the ODE. This is a third order linear ODE with constant coefficients. Okay, so now for all the higher order ODE, we just need to learn with the constant coefficients. Okay. All right, let me change back to my color. Okay. All right. So let me recall one thing before we start. So if you can remember, if we start with a y double prime plus b y prime plus c y, the characteristic equation is ar squared plus br plus c equal to 0. So the order of the derivative corresponds to the power of the r. Okay, but here we have y triple prime. Okay, the y triple prime will actually corresponds to r cube. So here we have 1. So okay, the characteristic equation is r cube minus 7. Y prime corresponds to r. And 6y, y corresponds to the constant term. Okay, so this is the characteristic equation. Okay, this is order 3 polynomial. Okay, we cannot use the quadratic formula to solve it. So how do we solve it? Use the rational root theorem. Okay, so use rational root theorem. First of all, we have to figure out, okay, what are the constant terms? Okay, the constant term is -6. So what are the integer factors of the constant term? Okay, integer factor of the constant term are, okay, start with plus or minus 1. Okay, and then plus or minus 2, right? 2 is a factor of 6. It could be also plus or minus 3. And then it could be plus or minus 6. So those are all the integer factors of -6. So far, so good, everybody. Next, we look at there's a coefficient 1 here. So we look at factors of the leading coefficients. Okay, factors of 1 is just plus or minus 1. All right, then the possible root is gonna be, you use the factors of the constant term over the factors of the leading term. So plus or minus 1 over plus or minus 1 is plus or minus 1. Plus or minus 2 over plus or minus 1 is plus or minus 2. Plus or minus 3 over plus or minus 1 is plus or minus 3. Plus or minus 6 over plus or minus 1 is plus or minus 6. So far, so good, everybody? Okay, so here, how many possibilities we have? Okay, so here we have 8 possibilities. Okay, so 8 possible roots. Let's look at this guy. This guy has how many roots? So this polynomial equation has 3 roots. Okay, and here we have 8 possibilities. So within those 8 possibilities, okay, if this polynomial has a rational root, then the rational root must be one of those 8 possibilities. Okay, and my second remark is talking about here we have 8 possibilities. Not all of them are the roots, because think about it, we only have 3 roots. Here we have 8 numbers. Some of them must not be the roots. Okay. All right. So which roots? So let's plug in. Okay. So we continue. So for each of the possibilities, we try it. First one, we try r. The root is r. So we try r equals to 1. How do we know whether this is a root or not? Okay, so let me call this guy the p of r. So we plug in our polynomial. So p of 1 is 1 minus 7 minus 6. What is that? Is that equal to 0? Well, that is negative 12, which is not 0. So if you put the number into the polynomial, then it's not 0, then it's not the root. Okay, so this guy is not the root. Next number, minus 1. We plug minus 1 in it. We get minus 1 cubed is minus 1. Minus 1 times minus 7 is plus 7. And minus 6. What happened? We get 0. Yes. So r equals to minus 1 is a root. Okay, so minus 1 is a root. What does that mean? It means r plus 1 is a factor of p of r. Right? Minus 1 is a root, then r plus 1 is a factor. Okay, so we can actually stop trying the list here, because we are given with degree 3 polynomial, okay, and we find a factor. R minus 1 is a factor, okay? That means that polynomial, which is degree 3, is a product of r plus 1 times another. This is a quadratic factor. Okay, so for the quadratic factor, we can find the root. So we can find the roots by the quadratic formula. So that's why here, if we have degree 3 polynomial, you use the rational root theorem. You just need to find one factor, one root. Okay, and then you can use long division to find the remaining quadratic factor. Okay, after that, you can either factor out the quadratic factor or use quadratic formula to find the roots of the quadratic factor. Okay, so that's why here, we continue. We have so we use long division. We have p of r, so p of r is, p of r is r cubed minus 7r minus 6. Okay, I don't have much space. Let me write smaller. Okay, that divided by r plus 1. Okay, so what multiplied by r gives us r cubed? So r squared. R squared times r cubed. R squared times 1 is r squared. Well, use the first line, subtract the second line. You imagine here that there is a 0 r squared. Okay? So 0 r squared minus r squared, we get minus r squared. And we have minus 7r and minus 6. What number do we multiply by r to get minus r squared? Minus r. So minus r squared minus r. Use the first line, subtract the second line. We have 7r plus r is negative 6r minus 6. What number do we multiply here? 6. So we have negative 6r and then minus 6. And the answer is 0. Okay. So that's why we get the P of r is r plus 1 times the quadratic factor is r squared minus r minus 6. Can we factor further? We have r, we want negative 3 and plus 2. That will give us negative 1 in the middle, right? So what are the roots? The roots are negative 1. We already know that. Here is 3 and here is negative 2. Okay, so we find all 3 roots. So actually you can see those 3 roots. Those 3 roots is actually within those 8 possibilities, right? Okay, so and based on the roots, you can see all the multiplicity is 1. Okay, we have 3 distinct real roots. Okay, so we have 3 distinct or 3 different real roots. Okay, so what is the general solution? Well, the general solution is then y of x is c1. Here we have c1 e to the minus 1x plus c2 e to the 3x plus c3 e to the negative 2x. Okay, and this is the general solution. But for our problem, because we have initial conditions, so we actually need to continue and solve the 3 constants C1, C2, C3. Okay, let's see. So we have 3 constants C1, C2, C3. We need 3 equations to solve 3 unknowns. Okay, so we plug in y of 0, and then we have C1, e to the 0 is 1, C2, e to the 0 is 1, C3, e to the 0 is also 1. So that equals 1. So this is y of 0. Okay, to find y prime, we actually need to take the derivative. So the derivative is C1, derivative of e to the minus x is minus e to the minus x. C2, and then the derivative of e to the 3x is 3 e to the 3x. And then we have C3, derivative of e to the negative 2x is negative 2 e to the negative 2x. So this is the derivative. We plug in y of 0 is 0. So then we get minus C1 times 1 plus 3 C2 times 1 minus 2 C3 equals to 0. Y prime of 0 is 0. Okay, yeah, so this is y prime. This is y. Okay, and second derivative. Okay, so we take one more derivative. What do we get? So we have derivative is c1 e to the minus x, right? 2 negative make it positive. Here we have 9 c2 e to the 3x. Here minus 2 times minus 2 is plus 4. And then when we plug in 0, we get c1 9 c2 and 4 c3 equals to 2. Okay, so we have 3 equations, 3 unknown. How can we solve it? Well, through a matrix. So the first equation, 1, 1, 1, 1. Second, minus 1, 3, minus 2, 0. Third one, 1, 9, 4, 2. You can see here the first column are the coefficient of C1. Second column are the coefficient of C2. Third column is the coefficients of the right-hand side. Okay, so how do we get rid of this guy? We use R1 add to R2. and we use minus R1 add to R3. You can see all the linear algebra come back. Yes, that's why we gotta learn linear algebra first, and then we learn first order differential equation, then we can learn higher order differential equation. So we use the tools of linear algebra to solve higher order differential equation. Okay, so 1, 1, 1, 1. When we add it, minus 1 plus 1, 0. 3 plus 1, 4. Negative 2 plus 1, negative 1. 1 plus 0, 1. Okay, 1 minus 1, 0. 9 minus 1, 8. 4 minus 1, 3. 2 minus 1, 1. Okay, and what's next? You want to kill this guy. Oh, do you see 8 is already a constant multiple of 4. So we don't need to make the 4 to be 1. Okay, we can just use minus 2R2 add to R3. 0, 4 minus 1, 1. 0, 8 minus 4. So 8 minus 8 is 0. 3 minus 2 times negative 1. 3 plus 2 is 5. And 1 minus 2 is minus 1. So see, we have action form. This is C1, C2, C3, right hand side. Okay, the last row tells us that 5, C3 is minus 1. So C3 is minus 1/5. The second row, 4, C2 minus C3 is 1. So 4C2 is 1 plus C3, which is 1 minus 1/5, 4/5. So C2 is divided by 4 on both sides, 1/5. Right? And what's next? We plug in the first row, C1 plus C2 plus C3 equals 1. So C1, C2 is 1/5. C3 is minus 1/5 is 1. So what is C1? Just 1. So finally, what is our final answer? So our final answer is you replace the C1 by C2, C3 by those numbers. Okay? So our final answer is y of x is C1, which is 1, e to the minus x, plus C2, C2 is 1/5, e to the 3x, plus C3, C3 is minus 1/5, e to the negative 2x. So this is our final answer, final solution of this differential equation. Okay? Alright, we mark. So we're solving higher order polynomial. So we use rational root theorem, okay, to find round roots. So this is degree 3, okay? So here, so if we have degree 3, then we use, okay. So if we have degree 3 polynomial, we use rational root theorem to find one root, okay, and then use long division. But if we start with degree 4, we actually need to use the rational root theorem to find 2 roots, okay? Because you find one root is not enough. After you divide it by that factor, you still have degree 3. Degree 3, we still need to use the rational roots again. So you just use the rational root theorem to find 2 roots. So remember, you use factors of the constant term over the factors of the leading coefficients. Then we have many possible roots. So try those numbers, and we want to find 2 roots. Okay, then degree 4, we find 2 roots, we find 2 linear factors, so the remaining factor is the quadratic. Okay, so then we can use long division to find the remaining degree 2 quadratic factor, and then we can use quadratic formula to find the remaining roots. Okay? So let's continue and look at example 2. So I strongly recommend you to try this problem first. And then let's go over together. So first, characteristic equation. So we have r cubed plus 3r squared plus 4r plus 12 is 0. Okay, so that is the characteristic equation. Alright, so this is degree 3. We're going to use the rationalist root theorem. And then, let me make it more colorful. Okay, we have constant terms, so factors of the constant term are plus or minus 1, plus or minus 2, plus or minus 3. What's the next one? Plus or minus 4. What's the next one? Plus or minus 6. What's the biggest one? Plus or minus 12. Yes, those are the factors of 12. And then, so the leading, then we have the factors of the leading coefficients, which is 1. Okay, so that is plus or minus 1. Wow, what are the possible roots? So the possible roots are plus or minus 1 over plus or minus 1. You can see because we use this guy over this guy, well, the answer is just gonna be the top guy, right? Because everybody divided by 1 is just that person, that number by itself, right? So plus or minus 12. Wow, here we have how many numbers? We actually have 12 numbers. We don't plug in all of them. Hopefully we try some and then we can find the answer. So let's try. Always try the 1 first. So P of 1. So let's call this guy is P of R. So P of 1 is 1 plus 3 plus 4 plus 12. And that is greater than 0, so that is not equal to 0. So R equals to 1 is not a root, okay? And do you realize because all the terms are positive coefficients, okay? So if you plug in positive numbers, your numbers is always gonna be positive, so it won't be 0. So we know that all the positive numbers, they couldn't be the roots. Okay, so that's why we try the negative number. P of negative 1 is negative 1 cubed, negative 1. And then we have plus 3 minus 4 plus 12. Okay, so we have here we have 2 minus, so we have 10. Right, everybody? So 10 is not 0, so minus 1 is also not a root. And then we try negative 2. Okay, why don't we try 2? Because we just said, because all the coefficients are positive, when you plug in any positive number, your answer is going to be positive. It won't be 0. So the roots must be negative numbers. Okay, negative 2 cubed is negative 8. 3 times 4. And then 4 times negative 2 is minus 8 plus 12. Okay, what do we get? Here we get minus 16 plus 12 and 12, 24. Obvious is not 0. Okay, so not negative 2. Okay, let's continue. Try -3. So it really depends on whether we are lucky or not. It might be we have to go very down below the roots, okay? So that's why when you plug in the numbers, also find the pattern. See, I found the patterns, the roots must be negative numbers. Otherwise, how do you're gonna try 1 minus 1, 2 minus 2, 3, and then -3. So you have to try more. So sometimes think more can actually save us some time. Okay, -3 cubed is -27. 3 times r squared is 2. And then -3 times 4, -12. Oh, can you see they cancel? They cancel. We get 0. Yay! R equals to -3 is a root. Okay, if this guy is a root, what is the corresponding factor? So r plus 3 is a factor. Okay, then we know this is degree 3 polynomial. Okay, so after we get one root, it's okay. We can use long division, right? We can stop the process of the rational roots. Okay, and so we have our polynomial r cubed plus 3r squared plus 4r plus 12. When use it to divide it by r plus 3. Alright, let's see here. We have r squared, so r cubed plus 3r squared, and subtract 4r plus 12. Well, that is 4. So what happened? So we get p of r is r plus 3 and r squared plus 4. Okay, so some students might ask, can we go along the list? Okay, can we go along this list and find all 3 roots? The answer is no. You might not have like all the roots are rational roots. Maybe some of the roots are repeated. If the roots are repeated, you're not able to see that by plotting in the roots, okay? Maybe the roots are complex numbers. So that's why you're not able to find all the roots simply just plotting in those numbers into the polynomial, okay? So that's why here you can see r squared plus 4 is actually an irreducible quadratic. We have, so what are the roots? Here the root is -3. This guy, when you solve r squared plus 4 is 0. R squared equals to -4. When you take the square roots, you get plus or minus 2i. Okay, so what is the solution of that? Well, the solution is C1. This corresponds to e to the -3x. Okay, so this is, how about the complex roots? So the complex roots corresponds to C2. So usually it's x to the alpha x but here the root has no real part. So that's why e to the alpha is like 0. So we don't have an exponential function factor. So we have cosine beta. Beta is 2. Okay, x plus C3 sine 2x. Alright, so that is our general solution. Okay, next, because we are given the initial condition, we need to figure out what C1, C2, and C3. Okay, so let's see. Okay, let me continue here. So, okay, so we plug in. So here, the initial values are at x equals to pi. So y is 1, y prime is 1, y prime is 1 as well. Okay, keep that in mind. So when we plug in pi, we get C1 e to the minus 3 pi plus cosine. Okay, C2, what's cosine? 2 pi. Well, cosine 2 pi is like cosine 0. Cosine 0 is 1. And what is sine 2 pi? That's like sine 0 is 0. And the answer is 1. So 1 is y of pi. Okay, oh, this is gone. Okay, so we get the first equation. To find the second equation, we actually need to take the derivative. The derivative of e to the minus 3x is minus 3 e to the negative 3x. And the derivative of cosine is sine. Sorry, minus sine. So we have negative 2 c2 sine 2x. The derivative of sine is cosine. So we have 2 c3 cosine 2x. Let's plug in. So we plug in pi. We get minus 3 c1 e to the 3 pi. Okay, minus 2 sine of 2 pi is 0. And then cosine of 2 pi is 1. So that is 1. So that's y prime of pi. Okay, so one more to go. That's 9 c1 e to the negative 3x. Here, the derivative of sine is cosine, but you have an extra multiple 2, so we have 4 c2 cosine 2x. Derivative of cosine is negative sine, but we have an extra factor of 2, so 4c3 sine 2x. Okay, we plug in pi. We get 9 c1 e to the negative 3 pi, and then cosine of 2 pi is 1. And then that one is 0, so we get 1, which is y prime of pi. So far, so good, everybody? Okay, so let's solve the matrix. Okay, let's see whether we have enough space. Okay, first equation, e to the negative 3 pi, 1. And no c3, right hand side is 1. And then second equation, we have negative 3 e to the negative 3 pi, and then we have no c2 and 2c3, 1. Next, 9 e to the negative 3 pi, negative 4c2, no c3, 1. Okay, Gaussian elimination. So, okay, we can see this guy and this guy are constant multiple of the 1 entry. So we use 3r1 add to r2. We use minus 9r1 add to r3. Okay, e to the minus 3 pi, 1, 0, 1. And then here 3, so 0. 3r1, so 3 plus 0, 3. 0 plus 2 is 2. 3 plus 1 is 4. Alright, and then 9 of e to the negative 3 pi plus, okay, so this is 0. Negative 4 minus 9 is negative 13. 0 minus 0, 0. 1 minus 9 is negative 8. So far, so good, everybody? Okay. And then, how do we get this guy 0? So, first of all, I want to make this 1. Okay? How do I make this 1? Well, I can use, we can use the 4, we can use 4r2 add to r3. Okay, so we have e to the minus 3 pi 1, 0, 1. Okay, so 4 times 3 is 12. So 12 minus 13 is minus 1. So we don't necessarily make 1 here. We can make minus 1. It works the same, okay? And then 4 times 2 is 8. 4 times 4 is 16 minus 8, 8. And then 0, negative 13, 0, minus 8. Okay? So we continue. Next, we want to get rid of that. So we use negative 13 R2 add R3. Okay, so what do we get? E to the negative 3 pi, 1, 0, 1, 0, minus 1, 8, 8. And what's next? We have 0, and here 13 plus minus 13 is 0, and then we have minus 13 times 8. So minus 13 times 8. What 0 is that? And then here we have minus 13 times 8 minus 8. Wow, that's the same as minus 14 times 8. It's okay, we can leave it like that because they will cancel later. We don't need to multiply out. So remember, this is C1, C2, C3. This is the right hand side. So last, okay, so oops, I mean this. Okay, so echelon form, right? So last row tells us that negative 13, 8 times C3 is negative 14 times 8. So 8 cancel, negative, negative cancel. C3 is 14 over 13. Yes, so plug in the second row. Minus C2 plus 8C3 equals to 8. C2 is then AC3 minus 8. So that is 8 times 14 over 13 minus 8. Okay, so here it's better to use our calculator. Okay, so we have 8 times 14 over 13 and minus 8. So the answer is 8 over 13. All right. And then we can continue and plug in the first row. So we plug in the first one. We have e to the negative 3 pi C1 plus C2. C2 is 8 over 13 equals to 1. So e to the negative 3 pi C1 is, oops, okay, is 5 over 13. So C1 is 5 over 13 times e to the 3 pi. We both sides multiply by e to the 3 pi to get rid of the e to the minus 3 pi on the left. So our final answer y of x is C1, 5 over 13 e to the 3 pi times e to the negative 3x. And then C2 is 8 over 13 cosine 2x plus C3 is 14 over 13 sine of 2x. So this is our final answer of this problem. Yeah, it's quite a long problem, isn't it? Okay, let's continue with example 3. Okay, so first step, the characteristic equation. So characteristic equation 2r cubed plus 11r squared plus 12r minus 9 equals to 0. And what are factors of the constant term? Is plus or minus 1, plus or minus 3, plus or minus 9. How about the factors of 2, the leading coefficients? The plus or minus 1, plus or minus 2. See, this example, the leading coefficient is 2. It's not like 1. So we have more interesting results. So the possible roots is use this guy divided by those guys. So plus or minus 1 divided by plus or minus 1 is plus or minus 1. Plus or minus 3 divided by plus minus 1 is plus minus 3. And plus minus 9 divided by plus or minus 1 is plus or minus 9. And then you use all those numbers divided by plus or minus 2. So we get plus or minus 1 half, plus or minus 3 half, plus or minus 9 half. Okay, we have 12 possibilities. So let's go through it. So this is degree 3. We only need to find one root. Okay, then we can use long division to find the remaining quadratic factor. Let's plug in 1. We have P of R is, so this is my P of R. P of 1 is 2 plus 11 plus 12 minus 9. Obvious, that's not 0. Okay, next. P of negative 1. So negative 2 plus 11 negative 12 minus 9. The answer is so negative, so not 0. Okay, who's next? 3. So P of 3 is 3 cubed is 27. 3 squared, 9, so 99. 3 times 4. Oh, the answer is so positive, so it can be this one. So far, so good, everybody. And let's do negative 3. So P of negative 3 is negative 2 times 27, so 54. And that is 9 times 11, 99. Negative 3 times 12, negative 36, minus 9. What is that? So this guy gives us negative 90. Oh, yay! We find it. This is 0. Ooh, good, good, good. So this is our root. Then we know R plus 3. So whenever you see R equals to A is a root, it means R minus A is the factor. Okay? Alright, so R plus 3 is a factor. Okay? So we can solve the process of rational root theorem and use long division. Which is 2R cubed plus 11R squared plus 12R minus 9 divided by R plus 3. So what multiplied by R? We get 2R cubed, 2R squared. And then 2 times 3, 6R squared. Okay, so use the first line, subtract the second line. 5R squared plus 12R minus 9. What multiplied by R? 5R. 5R squared plus 15R. That is negative 3R minus 9. Okay, so, negative 3. So negative 3R minus 9. Yay! So this is always 0. So always 0. Why? Because you say that factor is x plus 3 is a factor. It means the remainder is always 0 because you find the factor. Okay? If you get the remainder is not 0, so then go back to check your work. Maybe you get the wrong root. Okay, so let's continue. So P of R is R plus 3, and then we have 2R squared plus 5R minus 3. Okay, can we factor it? 2R, R, and then we want to have 5 there, so it's plus 3 and minus 1. That will give us plus 5. Oh, can you see those are the same? We can combine together. Oh, okay. So this is what we get. We completely factor it. And what are the roots? So -3 is a root with multiplicity 2. Okay, and the other root is 1/2. Okay, so actually we get a root with multiplicity 2. So another good thing about using the long division and find the quadratic factor, because here, for example here, so when you plot those numbers, you only know that whether those numbers are the roots of the polynomial, but you cannot tell the multiplicity. So if a root is a repeated root, you won't be able to tell by just plotting it into the polynomial. Okay, so that's why here we can actually see R plus 3 is like appeared twice in the factorization. So -3 is a repeated root. Okay, so how to set our general solution? Okay, -3 corresponds to e to the minus 3x. And repeat it. What does that mean? Repeated, you don't put the same, but you put an extra x in front of it for the repeated root. And then this guy, we have e to the 1/2 x. Okay. Let's see, do we have initial condition? Oh no! Yay! So that is our final answer. Okay, so you can see if the problem gives initial condition, we have to go through find the derivative, find the second derivative, plug in the numbers, construct a matrix, and solve the constants. So much longer. Okay, so let's look at the next example. So this example, we have degree 4. Okay, so degree 4. Okay, so degree 4, let's do it the same, but in this example we're gonna use the rational root theorem to find 2 roots. Okay, 1 root is not enough, so r to the 4 minus r cubed minus 3r squared plus 5r minus 2 equals to 0. Okay, and the factors of the constant term is plus or minus 1, plus or minus 2. The factors of 1, the leading coefficient is plus or minus 1. Oh, so what are the possible roots? Use this guy over this guy, so we just get plus or minus 1, plus or minus 2. So we have 4 possibilities. So let's try those. Let's try 1. So P of 1 is 1 minus 1 minus 3 plus 5 minus 2. Let's see. This cancel. Oh, we're so lucky. That is a root. Yay. Oh, but we 1 root is not enough. We need to find 2 roots because this is the degree 4. Okay, so minus 1 we get minus 1 to the 4th 1, and then minus 1 cubed minus 1, but minus 1 is 1, and then minus 3 minus 5 minus 2. Oops, this cancel is negative, so not 0. Next, 2 is 2 to the 4th 16, 2 to the 3rd 8, 2 squared 4, 4 times 3 12, 2 times 5 10, negative 2. Alright, what's that? So this guy plus this guy, 26. This guy give us negative 20, negative 22. So it's not 0. Okay? So r equals to negative 2. We actually need to go through all the numbers in the list. So p of negative 2 is negative 2 to the 4th, 16. Negative 2 cubed, negative 8, but there's a negative in front of it, 8. Negative 2 to the square is 4. 4 minus 3 is 12. Negative 2, so minus 10. Negative 2. Okay, this guy gave us 24. This guy gave us negative 24. Yay! They're equal. Luckily, oh, we get 2 roots. Okay, so 2 roots. This guy, and so what are the factors? 1 corresponds to factor minus 1. The other one, negative 2, corresponds to the factor plus 2. So this guy is factor of p of r. Okay. So we want to know p of r is like r minus 1, r plus 2 times quadratic. Okay, and we want to figure out what's that. Okay, so we want to use long division. But before we use long division, what is this guy? Okay, so this guy, r minus 1 times r plus 2 is r squared plus r minus 2, right? And this is our unknown. Okay, so we use r to the 4 minus r squared, cube, minus 3r squared plus 5r minus 2 divided by r squared plus r minus 2. Or if you want, you can use long division twice to divide it by the linear factor. But I think I find this easier. I combine them and I just use long division once. Okay, r squared, r to the 4 plus r cubed minus 2r squared. This subtracts negative 2r cubed. This minus this become negative r squared plus 5r minus 2. Okay. We get negative 2r, negative 2r cubed, negative 2r squared, negative 2r plus 4r. They cancel. This minus this become minus r squared plus 2r squared, so r squared. And then this side minus this, r minus 2. Oops, same thing, so 1 here. Okay, so the remaining quadratic factor is actually r squared minus 2r plus 1. Okay, are we able to factor it? Oh, yes. So remember, this is the same as r minus 1, r plus 2. And this guy is actually r minus 1 squared. Oh, we can combine them together. It's r minus 1 cube and r plus 2. Oh, actually the 1 is a repeated root. If we put it 3 times, right? So the multiplicity, so the root is 1 with multiplicity 3, and the other root is negative 2. Okay, what is the general solution? So 1 corresponds to e to the x, but multiplicity, so repeated roots, what happened? You just keep multiplying by extra x. Okay, so here, what do you put here? X squared. So repeated, each term you just keep multiplying by extra x. And then that one is c4 e to the minus 2x. Okay, yes. So this is our answer for this problem. Do you have initial condition? No, yeah. Okay, great. So this is our final answer for this problem. Okay. Next, we mark. You're gonna distinguish them. Okay, what's the first one? This guy means the multiplicity is n. So this is actually means r equals to 1 with the multiplicity n is a repeated root. But what is this guy? This guy actually you can factor it, okay? So you realize, first of all, you realize 1 is a root of it. So r equals to 1 is a root. Okay? And then there are other factors. So if you use long division, you use rn minus 1 and r minus 1. Okay? So, and here you get r to the n minus 1 times that is r to the n minus r to the n minus 1. This guy, subtract this guy, r to the n minus 1 and minus 1. So you get r to the n minus 2, and then you get r to the n minus 1 minus r to the n minus 2. So you realize, so this guy, you eventually get plus r plus 1. Okay? And this is the remaining factor. Okay? So so this guy, 1 is a root, but the multiplicity is only 1. Okay? And you're gonna expect there are some other complex roots. Okay. All right. So let's look at example 5. Example 5 is given the characteristic equation. Okay, so we already have the characteristic equation in a factored form. Okay, so based on the characteristic equation, we can then find the general solution. Okay, so the previous examples, we spent a lot of time to factor the polynomial. Okay, but this problem, actually, the factorization is given. Okay, so let's figure out the roots. So this guy corresponds to r equals minus 2 plus 3i, right? And because of square, so this guy, the multiplicity is 2. And then this guy corresponds to negative 2 minus 3i. The multiplicity is also 2. And then this guy, we have r equals minus 5, with the multiplicity is 4. Okay, so the total degree is 8. So degree 8 polynomial. Okay, so how do we set up the general solution? Okay, first of all, you know the conjugate roots always appear as pairs. Okay, so that's why if you see there's a root minus 2 plus 3i, then there must be another root minus 2 minus 3i. They always appear as complex conjugates. Okay, so that's why here, if we have a pair of minus 2 plus 3i and minus 2 minus 3i, our solution will be e to the real part, negative 2x, and then cosine beta, the imaginary part, x, plus c2, e to the negative 2x, and then sine 3x. Okay, so this is the complex conjugate pair will give us. But because the complex conjugate pair is multiplicity 2, multiplicity 2 means we're gonna have more, okay? Multiplicity 2 will, the effect will be you multiply by extra x to the term. Oops. C4x e to the negative 2x sine 3x. So when we have repeated roots, what we do is we're gonna have extra x. Okay, so this guys corresponds to this guys. So you can see here the degree here is like 4. So that also corresponds to, we have 4 constants. See, C1, C2, C3, C4, 4 constants. So degree 4 corresponds to 4 constants. So next, r equals to negative 5. that gives us C5 and e to the minus 5x. This is one root. C6x e to the minus 5x. Okay, and we should have 4 of them. Okay, so the next one is C7x squared e to the minus 5x and cx cubed e to the minus 5x. See, we have 1, 2, 3, 4. So we have 4 constants. All right, 4 constants corresponds to this is degree 4 multiplicity. Okay, and so this is how we, based on the factorization of the characteristic equation, how to set up our general solution. Okay, and that's it for this session. It's actually quite long, right? Have a good day. Bye.